What is up, everybody? Let us move towards the properties of binary trees now. I have another video in which I've talked about basics of binary trees, and I explain you about why we use binary trees and where you should use binary trees and what are the advantages of using binary trees. So I am using this Microsoft PowerPoint in order to present this as a slideshow, and it's actually very convenient, and I have this pen using which I can explain. So let us move towards properties of binary trees. So let me recap. This is the root node, and let me tell you one more thing. This is the left child of this binary tree, and this is the right child of this binary tree, and similarly this is the right child of binary tree, and the left child, if you implement it in C++, it's going to be null. So it's going to be a null pointer. I'll be showing you some codes later, but let us talk about binary trees right now. So the first property says that, let me write it down here, properties. I'm trying to make good handwriting. Properties. Let me write down one here. And first property is the maximum number of nodes. The maximum number of nodes at level L is 2 to the power L minus 1. 2 to the power L minus 1. So what does it mean? So if you are at level L, so assuming level of root is 1 here, so how many nodes can you have here? At max you can have 2 to the power 1 minus 1 is equal to 1. So you can have at max only one node here, and if I talk about this thing, L is equal to 2, you can have at max 2 nodes, and here L is equal to 3. You can have at max 2 to the power 3 minus 1, which is equal to 4. Here we have 3, but we can have at most 4. So we have 1, 2, 3 at this level. So this is level 3. So this is that is it. I mean, this is really very simple, and it's self-explanatory. So I hope this is you got it. So the level is number of nodes on path from root to the node, including the root and the node, and level of root is 1, as I already told you. Well, you can also prove it by induction. I'm not going into proof of this because this is really very intuitive. So let's move to the next slide and talk about the second property of binary trees. Maximum number of nodes in a binary tree of height h is 2 to the power h minus 1. So let us say height of this binary tree is h. Similarly we have, so let us say this is n is equal to 1, n is equal to 2. Similarly we have n is equal to h. So the height of the tree is h. Now here the height of a tree is maximum number of nodes on route to the leaf path. So this is the root. I forgot to tell about the terminology. This is the root node and this is leaf node. So this is really very easy, and I mean, I should not regret why I did not tell this previously. So let us move towards this again and talk about this. So height of a tree is maximum number of nodes on route to the leaf path. Height of a tree with single node is considered as 1, and the result can be derived from let me explain it. A tree has maximum nodes if all levels have maximum nodes. Obviously this is so obvious. So if you want this tree, a tree of height h, to have maximum number of nodes, then every level should have maximum number of nodes, and maximum number of nodes at a given level is I want you to speak up that you can't. So it's 2 to the power L minus 1. You can write comments though. So 2 to the power L minus 1 should be, I should sum it from L is equal to 1 to L is equal to H. So it's gonna be 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 2 to the power h minus 1. This is a GP, geometric progression. I know I don't want to write it, so let me now calculate sum of this GP. The sum of this GP is going to be 2 to the power h minus 1. 2 to the power h minus 1. Now I want to point out something here. In some books, height of a leaf is considered as 0. So sometimes they say that height of this is 0. I say it's 1. I mean, I read so many books and there in most of the books it's 1, but there are people who say it's 0 and they write it as 0, some authors. So we should respect both of them, and we should we should replace our h with h plus 1 in that case, and I don't want to confuse you here, so I'm going to stick to n is equal to 1 for root node and n is equal to h for leaf node. So let us move to third property now. Property number 3. In a binary tree with n nodes, minimum possible height or minimum number of levels are log n plus 1. Let me write it here. In a binary tree with n nodes, minimum possible height, height, I hope my handwriting is readable, possible height, or minimum number of levels, minimum number of levels is log to the base 2 n plus 1. Now how to calculate this? So this can be directly derived from property number 2 that I already explained you. If we consider the convention where height of a leaf node is considered as 0, the above formula can be it will be log to the base 2 n plus 1 minus 1. So I don't want to go to that notation. For me, n is equal to 1 is going to be a root node strictly, and you should also stick to one convention only. So in a binary tree with n nodes, minimum possible height or minimum number of levels is log to the base 2 n plus 1. Now you'll say why. So let us say minimum number of levels, minimum number of the minimum possible height. If you want to have n nodes, then you'll say 2 to the power h plus 1, or I should say 2 to the power h minus 1 is equal to n. So 2 to the power h is equal to n plus 1, and h is going to be log the base 2 n plus 1. So the h is going to be minimum possible height. If you want to have n nodes, you should have minimum log to the base 2 n plus 1 nodes. So this property is really very important, and again I have derived this assuming for root node n is equal to 1. So there are some more properties that I'm going to be talking about in next video. So let us talk about some more property in the next video. In the meantime, you can like this video, comment on this video in the comment section down below, and I'm gonna see you guys in the next video.